Hi, in this video, we'll talk about a slightly different way of looking at the Grover's search. It's called inversion about the mean. Now, we have looked at Grover's search as a sort of rotation in a two-dimensional space where each iteration of the Grover search, the Grover operator, actually rotates the vector by an angle theta towards the solution space. Now, this is a slightly different way. Let's start with just visualizing the amplitude. So I'm going to draw the amplitudes right now. So let's say that I have the initial amplitudes of the Grover search. Um, they're all of in equal height, which is 1 over square root of n, right? Something like this. So our initial amplitudes, they are all 1 over square root of n. And our state, psi, which is 1 over square root of n, summation over x. So this is our initial state. Now I can write the state psi as summation over x, alpha x, where alpha x are the amplitudes. These amplitudes are going to change when we apply the Grover iteration. Now recall that the Grover iteration consists of two operations. One is this u of f and other one is r psi. So u of f marks the element, and let's say only one element is marked for the sake of simplicity. So what does u of f do? It takes the marked element and attaches a negative sign to it. So let's do that over here. So we have, let's say this element is marked, then this is going to be a negative sign. So we have this, let me call this x star, alpha x star is over here, right? And then our r psi operator, so this one marks with negative sign. And what does this do? So this operation, one can show that r psi is indeed r psi is reflection about this uniform superposition vector. And one can show that r psi is takes alpha x. So it takes basically a state summation x alpha x get psi. And if you apply r psi, you get 2 mu minus alpha x. So it takes the amplitude alpha x to 2 mu minus alpha x. And what is mu? Mu is the average amplitude, summation alpha x over n. And the reason this thing is called inversion about the mean, that effectively, so when I first flip alpha x, the mean, the initial mean is 1 over square root of n. When I flip it, if I take the mean of all the states, then it will be shifted slightly downward, maybe over here. Right? And then R psi will actually, this operation will actually flip about the mean, or so it will sort of invert about this mean. So the amplitude will get amplified by reflection about this mean. So the final amplitude will actually end up somewhere over here. Let me just redraw this. right? So it is basically this height, which we see over here, is the same as this height, right? So it gets reflected about the mean. And so initially this is let's say minus 1 over square root of n. This height will nearly be 1 over square root of n. Why? Because if I take the mean of the elements after the reflection has been done, then it is n minus 1 elements with amplitude 1 over square root of n plus 1 element with amplitude minus square root of n. So this will be minus 1 over square root of n and then divided by n. So this will be this red line over here, which is going to be equal to 1 over square root of n minus 2 over n square root of n, which is nearly equal to 1 over square root of n, because I can ignore this factor. So this red line is not really far from the original mean. And so when I reflect about the mean, this is going up by 2 over square root of n. This is nearly 1 over square root of n. So my amplitude of the marked element, if I count, it is actually from here, the height is 3 over square root of n, right? So the amplitude has, whereas the remaining elements, the amplitudes will get reflected about the mean and it will go down a little bit. So after I do the reflection, the remaining elements will be over here somewhere. Okay. And then I repeat this process. So if I repeat the process again, then this 3 over square root of n will get first marked. So it will, this is nearly 3 over square root of n. In the second iteration, this will go to minus 3 over square root. So it will be much lower over here, somewhere over here. And then the mean we'll calculate, the mean will go further down maybe. And then in the inversion about the mean, this will end up being over here, which is nearly 5 over square root of n, and so on. So basically what's happening is that the Grover's iteration is amplifying the amplitude of the marked element by approximately 1 over square root of n each time. It's not always 1 over square root of n, but approximately that. And then one can show that in order of square root of n operations, we can get the mean up sufficiently amplified such that the probability of measurement of that marked element is high. Now one has to be a little careful over here. When the amplitude becomes too high, right, over here, then the mean of all the elements can go negative, can go over here, right? And then instead of amplifying, it can actually stunt. So one has to be careful to stop the iterations after appropriate number of times. But this is another way of looking at the Grover's search.